All right, look what I can do. Huh? How about that? It's just like watching Twitch, except it's chemistry notes, huh? All right, let's get this going. First off, note the joke in on the right. I think it's hilarious. We'll just let you chuckle on your own, and we'll get going. Okay, this is the mole. We're going to talk about molar mass, and I'm not talking about giant teeth. Those are massive molars. So be careful here. Okay. All right, we're going to move on to what you should be able to do at the end. We're going to be able to convert between mass and moles. Last time we learned about Avogadro's number. That's how we get to particles. This is how we get to mass. This is how we actually measure things in the lab. So this is going to be a big thing. We're going to convert mass to moles or moles to mass, and we're going to calculate molecules, moles, and mass given any of the other ones. So we're going to do some problem solving as well. All right, first to start, we're looking at different elements. What is molar mass? Molar mass is the mass of 1 mole of any of those atoms. So if you take a look at the picture in the bottom right, we've got all sorts of different elements. They are all different masses, but they all have the same number of atoms. They all have Avogadro's number of atoms, which is a lot, but you can clearly see that the sizes are different because their masses are different because some atoms weigh more than another. You'll see that 1 mole of carbon is 12 grams, 12.01 grams. That's the important one. It's the one we kind of define everything else off of. Uh, but regardless, you'll notice that these numbers you can see on the periodic table. So if you grab your periodic table, you look for zinc, you'll see it's 65.4 or 65.5, whichever one it is. 12 grams for carbon, 24.3 for magnesium, so on and so forth. Any element, if you have a mole of atoms, or 6.02 times 10 to the 23rd, it will weigh that amount in grams that are on the periodic table. So really quick, you can look for gold. You should get, I think it's 196.97. Chlorine, 35.45. Fluorine, 19. I've got all these memorized. You don't necessarily have to because you have your periodic table with you, but you'll do it so often that that's just going to be the case. Gotta remember, gotta keep looking at the camera because look at this cool stuff that I did. Anyway, when we're counting atoms, we're going to use a scale. So let's say I take this carbon atom. I'm not sure if you guys can see my mouse, so I'm going to grab my laser pointer. So let's say you have carbon here, and you put it on a scale, and the scale reads 25.4. What I can do with that is I can start counting how many atoms are in there, right? Oh, it doesn't let me click. So we'll have to go back here, unclick that. I'll check if you have the mouse later. To count the number of atoms, we're going to use the scale, like I said, and we're going to use this following conversion factor. Notice how it does not have Avogadro's number. We might have learned about Avogadro's number, but it's not the solution to everything. Here we have 12 grams of carbon is 1 mole, or 1 mole is 12 grams of carbon. And we do have that 0.01 at the end there because we are keeping sig figs together. Okay? So if I want to know how many moles are in that sample on the right, what I'm going to do is I'm going to put 25.40 grams to start because that's what the scale says. I'm going to put it in a fence post. Grams are going to want to go in the bottom, and that puts moles on top. So I'm using the conversion factor on the right to get rid of grams. Ooh, I can do this. We can grab the pen. We can go hiya, hiya, because the grams go away, and I'm left with an answer in moles, which I'm going to take 25.4, I'm going to divide 12, and I'm going to get 2.11 moles of carbon. So it's pretty straightforward. We're just going to use one of those conversion factors to convert between mass and moles. This one, I have copper instead of carbon, and I have how many moles it has. So I'm looking at this picture on the right, and there are 3.1 moles of carbon, or copper, excuse me, in that picture. The question is, if I put it on a scale, how much should it weigh? Well, if I have 3.1 moles of copper, I'm going to throw it into a fence post, but this time moles is going to go on the bottom in order to cancel it out. So this way, moles gets crossed off. Look at the, I got to work on my, mouse samurai because those clearly aren't straight lines, but that's okay. You'll notice that it's 63.55 instead this time. It's not 12 because I am dealing with copper instead of carbon. And so I'll multiply those two numbers together and I will get 197 grams of carbon, which is about a little less than half a pound. A lot less than half, maybe a third of a pound. Now, compounds. What if they're not elements? What if they're compounds? What if it's water? What if it's carbon dioxide? What if it's sodium chloride? Any of those? Well, the molar mass of a compound is the sum of the masses of its individual atoms. So what I'm going to do is, if I have water, I'll grab a laser pointer here. If I have water, I'm going to take 2 hydrogens and add an oxygen. And so that's 2 hydrogens. That's the number from hydrogen on the periodic table. And I'm going to add an oxygen to it for a total of 18. And the unit's really important here. It's always grams per mole. So hopefully you're taking notes alongside this. Make sure you write grams per mole there. If we have carbon dioxide, that's 1 carbon plus 2 oxygens. 1 carbon plus 2 oxygens, that's 44.01 grams per mole. NH3 is ammonia. Notice that there's 3 H's. I'm going to multiply it by 3. I get 17. Now it gets really difficult when you have these polyatomic ions and there's parentheses. You got to count them up. So you do have to realize that this 2 means that there are 2 NO3s for a total of 2 nitrogens and 6 oxygens. And then you just go through and do the algebra. You look up calcium on the periodic table, you look up nitrogen, you look up oxygen, and you multiply it by how many atoms there are, and you get a sum, 164. A lot of our sums will be between, the low teens and 300 or so. There are plenty of molecules with more, but we won't run into those too much because we are in first year chem after all. I do want to keep this as simple as I can. Oh, I got a next button. What do you know? So this is aspirin. You can see the picture on the right. And if you wanted to, you could count up each individual carbon atom, right? Each individual oxygen atom. You'll get a quantity of 9, 8, and 4. What I'd like you guys to do is pause the video real quick. Go through and actually count up what the average is, because these boxes here have answers behind them. But if you guys try it before and then check your work, we can find out if you guys really know how to find molar mass, or this is called molecular mass because it is the mass of one molecule as well, but it's a whole nother language difference. But anyway, go ahead and pause and I'll keep going. If you've paused already, done your work, now you can listen. Okay, so as I go through, we'll see that the masses for carbon, hydrogen, and oxygen, we can find those on the periodic table. When we multiply them by their numbers, so 9 times 12, 8 times 1, 4 times 16, these are the numbers we get. And when you add those together, you get a total of 180.15. What would the unit be? Grams per mole. In fact, that should have that on there. Let's write it. Grams per mole. Not bad. No, that's bad. It looks like it's kindergarten writing, but that's okay. So, overall, what have we learned so far? So last week, we learned how to go from moles to particles. So we use Avogadro's number on the bottom if we go from moles to particles. We use Avogadro's number on top if we go from particles to moles. Today, you learned about molar mass, the mass of 1 mole of an element or a compound. If you're going 2 mass, molar mass will go on top. If you're going 2 moles, molar mass will go on the bottom. Basically, what we're saying is whether we multiply or divide by molar mass given the path. And we can use this diagram, this entire diagram here, to help us plan out our solutions to given problems. Let's try it. On the right, I have some marble chips, which are calcium carbonate, and what I'm going to do is I'm going to put it into some hydrochloric acid, and what they do is they bubble up carbon dioxide. And this scale, if I tear it at first, it says 0, and sometime after the reaction, it says 0.74 grams. Negative 0.74. It means it lost 0.74 grams. Now, did those 0.74 grams disappear? No. Those are CO2 molecules leaving the solution. Let's see if I can show you guys here. So there's these bubbles right here, and they're actually leaving, going through the cotton, and it's all CO2 molecules that are leaving. So we can find out how much CO2 was actually released by going through and using molar mass. What we'll do is we'll plan it out first. Okay. Now, what measurement do we have? We have the 0.74 grams. So we are in mass right now. In order to get over to our solution for this, it's how many moles. We're going to go from mass to moles. And if I look at the second question, I'm going to go to molecules. So it's going from mass to moles to molecules. So what we're going to do is we're going to first go from mass to moles. To do that, we're going to take 0.74 grams. Wow, I bet you guys heard that one. My daughter is having fun up there. We'll just put it that way. 0.74 grams, and we'll put a fence post there. Grams will be on the bottom. I get 44 from carbon plus 2 oxygens, and I'll divide those two numbers, and I'll get 0.0168 moles of carbon dioxide. Now that's a measurement for the amount of carbon dioxide that's left. It doesn't tell me how many molecules yet. That's in moles. Remember Avogadro's number? So we'll use Avogadro's number to get over to particles. So in other words, all I've done is I've done this path. I need to do the second path to answer this second question. This is the answer for the first question, right? How many moles of CO2 was released? That many. So what we'll do now is we'll take the moles and we'll go over to particles. We'll take our answer from the first one, which is in moles, and we will convert it to using Avogadro's number. So this time, mole should go on bottom, molecules will go on top. There are Avogadro's number of molecules in 1 mole. Notice how it's always 1 mole every single time we do this. It'll help you guys out. So you do the math, and we end up with 1.01 times 10 to the 23rd molecules. Now, how many atoms are in this 6-gram sample of sulfur? Another problem, right? Notice that it says atoms, and it gives us mass. If we go to plan this out, we will see that we have a mass, but we need particles. So it's very similar to the last one, and we're going to shorten it just a little bit. Okay? So we have this, we've set it on a scale, essentially, and I want to count how many atoms are in there. What I'm going to do is I'm going to go from mass to moles, and then from moles to mass later on. So I'll put my 6 grams of sulfur there. 32, that's the molar mass of sulfur. You can look that up on the periodic table. In 1 mole, notice how grams will cancel out as we go along. But I'm not there yet because I haven't answered the question. I haven't said how many atoms there are. So what I can do is I can draw a second fence post as an addendum to the first one. Okay? And what I do now is I set it up so that moles is on the bottom. Or I'm going to particles, right? So I'll set that moles on the bottom of the second fence post. Particles, or atoms in this case, because we are dealing with sulfur, on the top. What it does is it sets it up nice and neat so that I can go through and cross out my grams using my samurai skills and cross out moles as well. So 2 crosses. And what am I left with? Atoms, which is what I wanted in the question. It's all about where am I and where am I going. So we'll take 6, we'll divide it by 32 because it's on the bottom, and we'll multiply by Avogadro's number for a total of 1.13 times 10 to the 23rd atoms of sulfur. One last problem, just because. This time I've told you how many atoms there are, and I want to know how much it weighs. So what we'll do, planning it out, we are going from particles to moles this time. We started in particles, we didn't start up here. So I'll start with my atoms, put it in a fence post. Atoms will go on the bottom, moles will go on top. Oh my gosh, I completely ruined this one. Wow, that was not in order. I apologize. So let's just start over here. We go from atoms. Atoms is on the bottom. We got 1 mole on top, 1 mole on bottom. The mass of silicon on the top, and I end up with 1.20 times 10 to the 25th divided by 6.02 times 10 to the 23rd times 28 gives me 560. Notice the point there because I am keeping sig figs as I go through. Watch out for that. All right, that's it. Good luck. I've got homework for you.